So this is just a short like electronics 101 prep for people who feel like they need some intro before like hands-on with actual electronic circuits. This is more actually a session about curiosity. It's about asking what questions you might have because I'm just going to talk about the basics of high school electronics, and everyone has been through this at some point in their lives. And it's more important about how all this stuff applies to what you're doing right now. Right? Like, so that intersection is what we should be talking about. I am just going to run rapid through, it's mostly a refresher through all of that stuff. Cool. Right. So the two important things, voltage and current are the two important things. They are the two important numbers. And can someone give me any intuition about what these things are? Even before we talk about definitions or anything like that. Anyone?
The voltage is something energy which is stored inside the battery.
Okay. But voltage is not only for batteries, right? So can...
I will...
Yeah, okay, sure. Yeah, so voltage is not only for batteries, right? Anyways, so can we... Next slide. Right. So this is a... how many of you have heard this analogy, the hydraulic analogy for water? I mean for electricity, like the water analogy, yeah?
Multiple times.
Multiple times, right? Anyone else have heard of the water analogy, right? It's like, so basically in that sense, we treat voltage as the height or the pressure of this tank, and you treat the current as the flow through a cross section of pipe. And they track closely to the definitions, the plain Newtonian definitions of what these things are, right? So your, if you want to think about it, electricity comes from electrons, and the kinetic energy of an electron is what voltage is, right? Like your potential, basically your potential energy of an electron is what a voltage is. And analogous, if you want to think about it, analogous to lifting a weight in a gravitational field. Right? So as you're lifting a weight more and more up, you are storing more and more energy in that. The weight is not fundamentally changing, right? The mass of this thing is still 1 kg. The mass of the electron is still the same. What its charge, it's like, its charge is also kind of the same. But what you're doing is you're lifting it in a potential well, which is analogous to lifting it in a gravitational well, if you want to think about it. It's actually a slightly better analogy than using this because this stuff it will break. Next slide, please. Yeah. So yeah, these are the ways that this analogy breaks. Electrons really don't flow forward. They flow at human timescales. They might as well flow at the speed of light. Like the interactions propagate at the speed of light. The reason I'm saying this like a lawyer or something and like really couching my language and making it very specific and not telling you that electricity moves at the speed of light is because electrons do not move at the speed of light. They move very slowly, and it turns out that we can really talk about the effects much more than what the actual object is, right? So it turns out if some of you are familiar, it would turn out that the electric field is actually the fundamental object, and not the electron or any of these things that we actually observe. And that's getting into too heady territory for electronics. So we just, even though electrons flow the wrong way, we just flip everything. And physics is okay with that because there's something called gauge invariance. As long as you flip all the signs properly, it's all fine. Right? So you can go forward or backwards, it doesn't matter. Yeah, there's no empty pipe. There's no such thing as zero energy even in empty space, right? Yeah. So that's the other thing is that also for this workshop, very importantly, all circuits need to be a loop, right? So everything needs to start from the battery, end at the battery, start from the power source, end at the power source. It can have multiple grounds, but each power to ground has to make a loop. Right, and that is a fundamental concept that I think will help you guys when you're building circuits. Yeah, next slide. Yeah, this is the one equation to remember. Ohm's law. It's a simple multiplicative thing. So this basically tells you how much energy if you push through the pipe, how much resistance you will get, like R, right? Can someone tell me about what's the difference? Like, what do you think about R? What is the difference between resistivity and resistance?
Impedance.
What? You told me another word I don't understand. I asked you two different, like, what's the difference between A and B? You said C. Yeah. So, R, like, see, so this is a equation. So, it's telling you that if I'm trying to push, like, there's a particular voltage difference, and there's a number of electrons that can pass through that, and R is what?
The speed bump.
The speed limit, right? It's the multiplicative factor that, like, it's the speed at which these things can, or like the resistance to flow that these things have. Now, because it was easier to measure it like this, we measured it in wires first. It's easier to measure it like this. But what you actually want is the conductivity, 1 over R. Yes. Yeah.
If you're assuming resistance is like speed bump, right? Basically, the speed limit.
Maybe speed is the wrong word to use. Yeah.
What's the difference between, say, R, which is resistance, and the cutoff voltage when it comes to like 0.7 and so on?
So that's the thing. That is a discrete stair step. This is a loss. This happens because the system is not ideal in many ways, right? Like, so what you're talking about, that jump, that discrete stair step that happens in a silicon transistor, is an inherent property of that thing, and it's a quantum effect. So it's either on or all or nothing. It's more all or nothing than this, because if you track the change of resistance over, like, so if it was a bulb or any linear resistor, it would be a 45-degree line, right? Which tells you that the more you try to push electrons, the worse this gets linearly, and this is a linear coefficient for that. Right. As opposed to it's a stair step. It like changes, a discrete jump. Yeah, a jump happens.
So those are semiconductors. These are.
Yeah. Right. Exactly. Yes. Yeah. Sorry. Yes. Exactly. So semiconductors versus conductors. These all Ohm's law works beautifully in conductors and pure resistive loads. Actually, excellent point to bring up, that they only work for resistors. Like, so ohmic heaters. The problem with Ohm's law in real life is that you have to add all the complicated things that components actually are. So they are also capacitors, they're also resistors, they're also inductors. But ultimately, without doing Kirchhoff or Maxwell's field equations or all of that, this is good enough for like most things, really. Yeah, next. Right. Yeah, so this is how you basically do a calculation of this. It's much more important that you guys have a intuition for how much these things change when like one of these variables change. So it's more that you are like, hey, so if I double the resistance, is my energy dissipation going up by 4 times? Is much more a thing that you have to think about, much more than like, 21 milliamps. These numbers you really have to look at when you are sourcing components, sizing components, resistors, all of these things, right? So this is the reason why you don't put a resistor in front of a motor directly to slow it down. Is that understandable? Because the moment the motor starts, it's going to pull it has a negative resistance. Because it's an inductive load. It's trying to pull as much current as possible. And the resistor is the only thing stopping it. And as much current as the battery is going to provide, that much is going to flow through the resistor. And that thing is going to fry. Right? So while once the motor starts, that's fine. It'll be fine. But just before it's going to start, it's going to fry. So Ohm's law gives you those kind of thing, because it's not only about how much current flows through a resistor, it's how much time it flows through, right? The total energy dissipated across this thing. So it's not only, that's how lightning strikes are survivable. It's not only about current and voltage, it's current, voltage, time. Sorry about that. One more number. So it's time also matters. Total energy, how much is delivered into the object. Next slide. Yes, the switch. Can someone please tell me what a switch is?
They close the circuit, the loop you mentioned earlier.
What?
To open the circuit, close the circuit.
Sure. So to open the circuit, close the circuit. It's an let's consider it now. A switch in common parlance is electromechanical. Yeah, it's an electromechanical part. It does both. It has a rocking or push button, or there are various switches. So because it's electromechanical, but how we think about it in circuits is exactly like this. It opens and closes the circuit. Which means what? When you open it,
The loop is broken.
the loop is broken. And when you connect it, the loop is connected instantaneously.
Almost instantaneous.
Almost instantaneous. Yes. So there is something about debounce. Next slide, please. Right. So this is what we think thing is, right? Like, so yeah, you attach it to say a pin of a microcontroller, and you open it, 0, you close it, 3.3, or whatever the voltage of the battery or microcontroller is. Next slide, please. Yeah, this is what you are talking about, right? The gentleman here, and almost means this, that actually because a thing is an electromechanical thing and it's actually a spring, ultimately it's a spring and it's a contact, and the switch's contacts are not clean, they are imperfect surfaces. When they're about to meet, they will bounce a little bit, and that bounce will show up as electrical noise. Okay, and this is around a few milliseconds actually. It's not very big. It could be microseconds depending on the size of the switch and all of this, but it's bouncing. Next slide, please. So yeah, you could solve it in code, right? So you will write a straight piece of code like this, which doesn't have debounce, and you get all sorts of random inputs, because your while the thing is actually connecting, your input is floating and not for a bit, and it's just bouncing on this. And you guys, there are videos of relays making contact, and they actually spark when they shut, right? And those of you who learned about inductors will know that once you have detached an inductor, the voltage goes shooting up, right? So as it's detaching, there will be an arc trying to form to like continue that. Like, so if the voltage is high enough, as the thing draws back, the arc forms to continue that, because ultimately the magnetic field doesn't want to change. So next slide, please. Yeah, so this is one way to do it. You could have a divider. Basically, you pull the switch either high or low when it is not being used. So that prevents stray electrical currents from activating your GPIO, right? Also, you can add a capacitor, so that will kind of smoothen out the ripples of your bouncing. That's one way to do it. This way, at least, so this is the resistor divider is actually a much more interesting thing to do in hardware than the capacitor. Next slide, please. Yeah.
Oh, this resistor one more, because V equal to I only something like that. So I will also jump. R is linear.
Right. R is linear, but you can set it such that you go back, please. So we'll talk about resistor divider. Can I just loop back to that? Yeah. Okay. 1 minute. This next slide, sir. Yeah. So no, next slide. Yeah.
About the previous slide again, if you want to look back, we can do it later, or I can skip.
Yeah, please.
Yeah, so about capacitors in general, so they are two separate conductors separated by dielectric, right?
Correct.
Isn't it technically the loop never completed because there is a space in between?
It's not completed. So it's not completed. You can think about it as it's completed intermittently.
Okay.
Right? Like depending on, so if it is DC, the capacitor is just going to charge and it's never going to discharge as long as the loop state does not change, right? But if your AC, you have AC or pulsed DC and your DC level is changing, then the capacitor is going to try to fight that. is a way to think about it, right? Because yeah, they're kind of the opposite of each other. And it'll become So this, right? So
It is just like
right. So you could fix it in software by adding some delay, and you can also turns out modern microcontrollers have internal pull-ups. You don't even actually have to add an external resistor. It's always best practice to do that because the internal pull-ups are of maybe 10K, 50K, something like that. But if you care about power efficiency, you want your pull-ups to be like 100 meg or something like that, because the amount of current flowing through that pull-up you don't want to be a lot. So that's another reason why you don't want to use internal pull-ups if you can avoid them. But if you want, like again, if you want to blink an LED and it's powered by the wall, it doesn't matter, use an internal pull-up or a internal pull-down.
Wait, by show of hands, how many here don't know what a K means? When he said K, how many here don't know what it means? Can you raise the hand, please?
Okay?
K.
Yeah, okay.
Can you go on the reach them the color code?
Oh, yeah. You'll have to please open a website with the color code. No, I didn't have the color code.
It takes you to 5 volts, 3 volts, project.
Guys, you can do a thing on your laptops or phone, right? Just search for registered color code chart. Just open the button.
Yeah, the first one.
The second one. Color code.
Yeah. Come on. No, to basically say that these things. Yeah. So usually resistors have right. So R is the unit of resistance, like, right. So you have ohms discovered by Georg Simon Ohm, and this. So we use it, the Greek letter omega, and you have a discrete stair step. So the resistors are usually marked with bands. They're small enough where you really can't print the number on them. And like even smaller resistors exist which use number codes and all of this. But like this is a color code, and this has been used for almost ever. And it might look intimidating and kind of, but like I would more account it to learning hexadecimal, right? You don't memorize. Some people, I'd be happy if you guys could like memorize it at one shot, but also there's the other way of just using it enough to that you know that like it becomes intuitive. And that's what happened with me and resistors eventually, is that like I think most people who are like get to work with resistors a bit will just look at a color code and tell you like this is what it's this. Now yes. Yes, there is many mnemonics for this. Roy G. Biv. What?
B.B. Rao.
Okay.
Went for a gatherings.
Well, okay. So there are mnemonics. So to me, it's kind of it's like the emission spectrum. It's easier for me to remember it like that. It goes from low to high energy. So, anyways, whatever you want to use to remember. Yeah, right. So then you have these bands, and then you have the first where is that? Yeah, the first 3 bands will tell you the value, and then the multiplier, and then the tolerance. Okay, and the tolerance band actually is a little iffy because sometimes some resistors don't have this tolerance band depending on what resistor it is. So then the first it'll tell you like, so if this is red, so it's 2, and the second number is 3, and so it's 23, and your whatever, so it's
This is a 4 band.
Yeah, 4-band, no? Yeah.
Ignore the third.
Yeah, why? Okay, anyway. So, okay. Usually it's just these 2 bands and the multiplier, right? It's a 3-band thing. And so you have so it's 3 into ohms. So it's 23 ohms basically. And then you have your tolerance band, which is like 5. No, 1%. Yeah, 1%. Yeah. So, but usually it's 3 bands and the tolerance band. The first 2 bands tell you the number, and then the other band tells you in scientific notation how much you should multiply it by. Right? So it's like the same thing as this. Right? So these colors always mean the same number. It's just 10 to the power 0, 10 to the power 1, 10 to the power 2. Right?
Silly question.
Yeah.
What if what if the resistors reverse?
That's why this tolerance band is really useful. If you know if you know which side it's on, and it's usually gold or silver, because it's going to be 5% or 10%, or 1% if you're really like using nice resistors, you can at least by that you can orient yourself.
But what happens if you do put it down reverse?
You put nothing.
But it doesn't have polarity.
It doesn't have polarity. Right?
You loads it.
You don't blow the circuit. It doesn't matter. Like he's talking about how do you read it right?
Yeah.
How do you key it that you read it right?
The longer in the
It's a resistor. It doesn't. They don't cut it usually like that. Measure it with the multimeter if you're confused. Yeah, SMDs you will have to like either like if you lose it from the packaging you have to measure it. There's
a pattern to see that.
Yeah, there is a color gap also. Yeah, you're correct. So the tolerance band always has a large gap towards the end. But again, just given the variances and like manufacturing tolerances, it's a little iffy. I've seen many resistors that don't follow this convention at all.
Can someone try telling what colors 10K resistor will be? Someone who doesn't know. Someone will be quite careful.
Bro, I genuinely do not. I need the multimeter every time.
That's good.
10K, right?
Yeah. That's right. Right, 10K.
First 2 numbers into multiplier basically.
I have it in.
Hey, yeah, okay. 100K for you then.
Brown, black.
Sorry,
Yes, and,
okay, 10K resistor. Let it try.
Yeah.
10K, bro, try.
So you start with the 10K multiplier, and 111 is my first. That's what I start with.
So
Hey, no, don't.
ignore the third band. Okay.
Oh,
Ignore the third band. Just ignore the column. So 10K, what would it be? Okay, what would the first color be? Let's start with that.
brown for sure because one.
Okay, brown. Next one.
Brown, X and one on. Yeah.
Okay, wait. One at a time.
Brown,
Wait, sound it. Let them try.
Brown, black, orange. Okay.
Wait, let him try. Can you tell brown?
yellow.
Brown, yellow. Okay.
That's my guess.
Okay, brown, yellow.
3 bands. At least minimum 3 bands.
I'm saying ignore the third band there. Because that's 4 band there.
not the fifth band.
No, the 5th band is the tolerance band. 4th band here, this one. Like this one in the middle actually, the 3rd band. It's
The third thing is throwing.
yeah, please. It's throwing me off, dude. No, we'll show you the right band. Sorry.
We'll give you a better one.
Yeah, this is sorry. Yeah, that's much better. This yeah. You're doing it on the fly, man. It's fine.
Okay, look at this Okay, wait. What's the first color?
First color is brown.
Okay.
Next it's black.
Okay.
Then color bright.
Third band is the multiplier. So
Multiplier. Like,
so 1K is sorry 10K is 10 into 1000.
are you using like 100 or 1000?
1000. Okay, 10K. What? Yeah, so brown, black, orange. That correct? Yeah, brown black.
Yeah, brown, black, orange.
Brown black. 10 to the past 3.
10 years, right?
Yeah, 10K is under 4. 10 is not 10.
No, if you're in
Black. It's brown, black.
Yeah, you're right. Okay, wait.
Yeah.
Bro, you try 220 ohms.
Hmm.
So wait, how does it work? Like, it can be 20, red, black,
Oh, God.
orange.
220. Right.
And I want 560K.
Red. So stand for brown.
Try it. First batch, 220, right? So break it down into like this. 22 into multiplier. So 22 into what is 220? Okay, so where do you get, how do you construct 22? You can have two repeating colors of the same band.
Yeah.
Right? So what will make 220? Not black, bro. Sorry. Try again. What is 2 first?
Red, bro.
Sorry, be red, but where there's a certain how would it, which one should come first?
There's no, anything can come first. Right?
Yes.
See, look at, break it, see. First 2 digits into multiplier. So
It's in. So you guys learned scientific notation, right? You compress it into one number into 10 to the power something, right? So this is 2 numbers into 10 to the power something.
So red.
yes.
second digit will be
You can't do brown again. No.
you need to write.
I'm very confused, sir.
So in color, I don't know, like break.
Yeah. So if you're talking about 220 ohms, right? So 2 into brown. So 22 into 10, 220. Yes. Red, brown.
Sorry.
Yeah. And yeah.
Wait, you raised your hand, right? You've never done this before? No. Okay, why don't you try 470? Kinda. Sorry, but I have to.
No, but I mean, like the thing is, for me, I get a visual for what 470K looks like, so it's fine.
No, I know that.
Yeah, that's all.
Sorry.
Yellow, violet, bro.
Yellow, violet, yes.
No, not down. Orange.
Yo, let me
Yeah. K.
Okay.
There's no way.
I said 470K.
Okay. Yellow, violet, orange, orange.
Yes, Wait, back.
No, if I go 7, you end up by
Yellow, violet.
Yellow, orange. Yellow, violet, orange.
Yeah.
No, orange, yellow.
Yellow. Because it's into 10,000. 47 into 10,000.
Yellow, violet, yellow.
47 into 10,000. 47 into 10,000, right? So 470K. You get only 2 numbers. That's why it's like scientific notation. You have to move it. You have to move it to the exponent if you're if you're more than 2 numbers. Right? So we say it as 560 ohms or whatever, but the 56 is the important bit.
Brown, green, and brown.
What is black?
Green, blue, black.
What? Wait, what is it?
He said green is fine.
5. He said 560. So it's, yeah, this.
Blue and white.
Green, blue, yellow. Yellow. 560K.
Yeah, no, 560.
No, 560K.
Just
Green, blue, yellow. Whatever. Yeah, this part is the scientific notation bit. Okay, slide please. We'll go back. Okay, just finishing up. There were just some questions about like pull up, pull down. We'll just finish that stuff. That's it. That's mostly what I had to say. Yeah. Next slide. Next slide. Next. Yeah, so GPIO stands for general purpose input output. Most of the so you can look at your most of the time most pins are more.
He's speaking important stuff.
Yeah, so this is the GPIO is most of the pins of a microcontroller that you will interact with. These are the pins of a microcontroller like the Arduino that are user interactable, right? Not all pins of a microcontroller are GPIO sometimes. Sometimes they're only input and sometimes they're only output. But those are rare. because we have built microcontrollers for so long, most of the pins we have standardized into a GPIO format, which is each pin can either be an input or output, and you can assign that in software. Yeah, next. Right. So if this is where all of this comes into the debouncing and why we need pull-up resistors and all of that, right? So you're right, to debounce we don't need pull-up or pull-down resistors. Yeah, but noise. So electrical noise. So every wire is an antenna, right? What is an antenna but a long piece of wire, right? So if your wire is long enough, you will start receiving electrical noise, and if you're listening at high enough frequencies, you will start receiving electrical noise on the wire, and like, of course, right? So human bodies have capacitance. So when you touch a circuit, you are introducing some capacitance between ground and the circuit itself. So all of that, like, because you are saying dielectric, right? We are a dielectric also, right? So that's the reason. The reason why we want a pull up or pull down, because usually if you just leave this and just listen to this pin, and if you just read the analog voltage here, so there are two types of reads, right? So this is a digital read where it's 1 or 0, right? So the thing is going to read whether it's on or off and nothing in between. Next slide. Just go back, sir. But actually, there is also another way you to read, which is analog read. Right? An analog read will tell you what voltage it is between the 0 and 1. So if it's 0 and 5, it's going to tell you what voltage it is in between. Now, the thing is that always it's analog, right? The world is analog. So it's always, the voltage is always bouncing between various places. And so in something like, say it's a 5 volt system like an Arduino or something like that, 0 to 5 volts, 2.5 volts will be the actuation point, like the logic level high, right? So once you've reached 2.5, it's going to read it as logic level high. So if you are stuck in a place where your circuit is maybe 2.3, or it sees a stray 2.5 volts for just for a few microseconds, it's going to read that as a high. Even though you just touch the pin or something like that. Nothing has happened. Yeah, next slide. Right. And the real reason for that are things called like impedance and all of that, is about how much electricity you need to drive into a load. And that is a thing that is best learned through practice and then come back to the theory and see why those things blew up. But yeah, impedance is a thing. So you can have a pull-up or pull-down resistor depending on whether you want your switch active high or active low. Does that make sense? So what is active high and what is active low?
When you're operating at high end, you pull it down every time you need to have a change.
Yeah. So no. So your active
Default, default.
Yeah, default high, default low. So I say active high, whatever, whichever way. Yeah. So default high, default low will be the opposite of what I'm saying, right? So default high, meaning that the resting state of the system is high. So that would be active low. When you activate it, it goes low. So the GPIO reads 0. But this decision can be made at each level. Okay. So your switch can be active low. Your GPIO can also be active high or active low. You can put a transistor in between the switch and the GPIO and have that active high, active, like, right? So it's very much, so it's a question of whether you are going to enable it or disable it by default. Here the pins are input. The pin is taking an input to the switch basically. So the pin is going to read whether this switch is high or low. Next slide. Yeah, so this is using a pin as an output. So when you connect an LED directly to a microcontroller, the microcontroller pins can only give so much current. Right, so it's only 20 milliamps. I wouldn't pull more than 20 milliamps out of anything. And 20 milliamps, yes. I'm saying that when you connect an LED as an output to a microcontroller, so can you just look up a thing of LED graph, like LED voltage graph? There'll be an exponential graph. Yeah. So active low means that the switch is always connected to the VCC by default, and when you push the switch, the circuit pulls it to ground, and so the microcontroller reads as 0. Otherwise, it always reads as 1. So when it's looking for when that goes to 0, then it like says that the state has changed. So that's an active low. Active high is the usual thing where it's off all the time, and then you press and then it goes on, and then the thing reads it as on.
Is that
No, yeah, okay, this is good enough. Yes. Can you say resistor versus LED graph? That's like a more illustrative. Yeah, this one is also a good thing. Yeah. So, yeah, this works. That yeah, okay. Yeah, almost done. Yeah. So this is your voltage versus current graph. Okay. So if this was a resistor, this would be a line, right? So as you give more current, you get R times more. Like as you give more voltage, you get R times more current, right? So it's like it's a 45-degree line with R as a factor. Now the problem with an LED is it's a discrete, like it's a quantum mechanical messy device. Like Harish brought up that it's a messy device that like switches on immediately, and this is the switch on part. Before the diode switches on, and it's like you can see that like as you're increasing voltage, current is not increasing by much. But at the point where this thing switches on, so each of these is for each color of LED, and from basic physics, there's an equation E is equal to HF, right? E is equal to HF. Like each electron has an energy that is dependent on its wavelength, right? And that's a fundamental. So if you are making red light, if you're making blue light, you have to put more energy per photon than red light. And that shows up as a difference in forward voltage. Some of this is the construction of the device, but some of it is also just because physics. Right? So this shows up as so if you just switched on an LED and didn't limit its current, it would just go towards infinity. It would keep trying to draw more and more current. This is called thermal runaway. Every microprocessor, everything does this. And that's why stuff needs to be cooled. Right? Because everything has a positive temperature coefficient. As this thing goes up, it's going to get, the resistance is going to drop and the current is going to go up, which causes it to heat up more, which causes this to go up, which causes the resistance to go down, which causes the current to go up more. Right? So this, unlike a resistor that's going to get more resistance as it heats up and then eventually explode, this is going to get less resistance, more efficient as it heats up and then eventually explode. And that's why if you just connect an LED without anything, it's just going to blow up. So just be careful when you're connecting. Just the slide, please. Yeah. Just be careful when you're connecting it to a microcontroller. You will have to add a resistor either as a source or a sink. So right now you don't have to worry about the difference between a source and a sink. It's just important that you're not pulling more than a few milliamps from the microcontroller. So calculate your LEDs based on that. So usually these LEDs are for 20 milliamps, but they'll be bright and indication. You can do indication at 5 milliamps also. It's not really that you have to drive them at full current. Next slide. Next slide. Yeah, that's it. Anything else? Any lingering questions? Any?
Yeah, it's Q&A.
Yeah. Yeah. So we are using it so that you don't read stray voltages on the pin otherwise. So if you are, say I am, so I'll give you an example, right? Solid example. So I have a watch, I make a watch and I am looking for the button inputs of that thing, but it's on my wrist. So if I just if I don't ground it or if I don't pull up, pull down, and I don't say that internally that you only look for the change of state. You don't constantly keep reading the spin. You just look for the change of state, right? So while it is 0, you do this. I'm changing the structure of the program a little bit because I want to read, ideally I only want to read the state change and I don't want to read the bit every time, like I don't want to keep polling. I want to read a state change.
So you put the
Yeah.
pull up register.
Yeah.
So I feel 5 volt.
Yeah.
When I press the switch, it will start reading 0 volt.
It'll read 0 volt. And okay, so that is the thing about, I'm sorry I didn't get to explain that, is this resistor dividers, right? So basically, if you have a resistor and you make can we go back to, yeah, this slide, yes, thank you. So if you have a resistor divider, you can imagine 2 resistors here. So if you have 10K and 10K here, right, you will have 1.5 volts here, right? It will divide by half, divide by it'll be whatever, like equal to 1 over this or 1 over that plus 1 over this, right? So it's somewhere in the middle of these two. It's not exactly, it's the median, whatever, right? What is it? What is the, average. Yeah, it's the average. Yeah. It's the average. Yeah, it's the average kind of these two. But so that's why you, depending on how you select this resistor, that tells you how much current will flow from here to here when you close this, right? So if I close this and at 3.53 volts at 10K, a few milliamps will flow through this. But if I make this 100K, then less current will flow through this. The idea is that this makes sure that any stray current that's going through this is not enough to actually push this pin one way or the other. You need a lot of current flowing for it to change state. Yeah, that's it. I can explain, we can talk about it later. Yeah.
The transmission milliamps.
Yes.
Now, how does it do that in the case of the capacitor? How does it regulate the flow?
Okay. Okay, in this, you wouldn't use a capacitor for this.
Is it right?
Yeah.
You said whenever you should put a resistor.
Yeah. Yeah. So the capacitor, what it does, it prevents the voltage from fluctuating up and down. So if you end up in a situation where you think that once you close a mechanical switch, it's bouncing and you can't wait for it to stop bouncing, you can add a capacitor so that when it is bouncing, that capacitor will try to normalize the ripple.
What I realized. Capacitor is supposed to charge.
Yeah. Right.
Let's understand.
Yeah.
In this case, how do we set it up such that it charges and then regulates the voltage, given that it's fluctuating?
Correct. So you would basically have to calculate how. So in this case, so can we go back to that third slide? We can definitely talk about this later also because this is right.
So yeah.
Yeah. Any other questions? Yeah. So this is the slide I was talking about. So basically you would calculate you would see how long this time was and you would pick a capacitor that charges within this pulse ideally, right? So by the time this pulse has happened, the capacitor is also charged, and when this pulse is gone, then it's discharging more like a 45-degree line than a straight, right? So it's more about, you have to think about that the capacitor is also doing a sine wave thing. And then that gets superimposed over this. And the addition, like what you get as a sum is the final, what looks like. Right? Yeah. Thank you. Yeah, thank you. That's a great question. Yeah. Any other questions?
Good question. Singing sounds like a really bad idea to me.
Yeah.
Is it?
What? Syncing into the microcontroller. It's a bad idea, maybe, sometimes. I don't, usually in most situations doesn't matter. Because like the power and ground planes of a microcontroller are usually equally well designed. Right? Yeah. Right. So I am still, I mean, I honestly, this is a question that I have as well. There are definitely situations where it matters to think whether you're sourcing or syncing. Usually that matters when you're connecting LEDs to like maybe like a shift register or something like that, and that has maximum sync ability to source or sync, right? So you should think about it if you ever have to think about the transistors of the microcontroller, right? That's where you think about the sourcing and syncing, because it's happening at the it is training the gates of that. Yeah, right. So it's about how much those gates can take. So if you are in doubt, just put a transistor in between. Easy. So that you have a bigger gate that can take more current. Yeah, I think that's done. Thank you. Thank you so much. Thank you so much for your attention. Yeah, thank you.